Hello everyone and welcome back, and this is the third part of this video. And in this video series I was sharing my experience of porting mbed-TLS to my platform, and this platform is based on STM32 microcontroller. And for the Ethernet controller I was using W5500 and its associated driver, that is the internet offload driver, which is provided by Visnet, the company which manufactures this chip, that is W5500. And since the video was getting very long, I decided to split the video in various parts, each being about an hour long. So now let us continue with the third part. So here you can see the data that I have captured from my serial port or the UART port. So these are the debugging messages that my microcontroller were sending, and since this message was very long, that is why I have to use the capture mode of real term. Here we have the real term. This is a serial terminal application used to view data from virtual COM ports. And since this black area, this terminal area, is very small, I cannot display all these long messages over here. That is why I have used the capture function, and all the data captured from my microcontroller is here. So in the last video we stopped here, and our mbed TLS was returning this error, and this is a fatal alert message received from our peer. And in this video we are going to solve this problem and complete this porting of mbed TLS to our STM32 platform. And to analyze this error and find a solution, we have to do first we have to have a deeper insight of the SSL and the TLS protocol. So let us start. For that I will recommend you a website, and the name of this website is this one, that is tls12.xorgs.org. So let us open our web browser and go to the URL, and here you can see that the illustrated TLS version 1.2 connection, every byte explained and reproduced. So from this website we can have a insight of how the TLS protocol actually work. What is the meaning of every bit and byte that is exchanged between the client and server. So now let us begin. So from here that we can see that the very first step is the client hello, or the client sends a hello message to the server. So in this case our STM32 is the client, and it is sending it is initiating the connection to our secure server. That is why our client will be sending the hello message, or our STM32 will be sending the hello message. So now let us see what is this hello message. So the session begins with the client saying hello. The client provides the following: the protocol version. So this is the protocol version of the TLS which the client can support. So in this case we are because we are beginning with TLS, I am not going for TLS version 1.3 because it is too much complicated, and that is why I am going with TLS version 1.2 for simplicity. Later on we will move to TLS version 1.3 also, but for starting I will recommend going for TLS version 1.2 because this version is still not depreciated and it is in use, and most of the server also accepts a TLS version 1.2 connection also, so this is not a problem. So the session begins with saying a client saying hello, and the client provide the following during this phase. The first thing is protocol version, the second is the client random data, an optional session ID, and important the list of cipher suites that the client can support. So there are various cipher suites or various algorithms for encrypting data, and different algorithms for signatures, key exchange, and that all those things are contained within this cipher suites. So Client can only support certain cipher suites, so it tells the server that I can support these cipher suites, so please select one of them so that we can start the communication. And in the same way, the client also sends a list of compression methods that it can support. Currently we are using a very low cost microcontroller with very small resources, very small amount of flash and ram, and also processing speed is not very fast compared to a full PC or a smartphone. That is why we will omit compressions, we will go without any compressions. So the default mbed TLS, it does not use any compression. And a list of extensions, we will leave this thing, a list of expansion, for simplicity. So it is something in form of like this, the bytes are sent something like this to the server. So let us click this annotation button to see the meaning of each and every byte. So as we can see, the first one, this thing, that is the 1603, or please note that all these are hexadecimal digits, they are not decimal. See here, a5, so obviously this is not decimal number. A1, so these are all hexadecimal numbers. So the first one, and 1 2 3 4 5, this 5 byte, this is the record header. So all the communication in TLS occurs in form of records. So this is the record header. So what is coming in the record, so the header identifies what is coming in the record. So the TLS session are broken into sending and receiving of records, which are blocks of data with a type and protocol version and length. So the first 16 here, type is this 0x16, and the 0x means hexadecimal in C programming language. This 16 means a handshake record. Okay, so we are doing handshake, so this is expected, very much expected. And then the protocol version, this is a bit confusing area. Here the protocol version is 3.1, also known as TLS version 1. So actually the TLS version 1.0, it is encoded like this, 3.1. Okay, and in the same way we have to see after that, if it is 3, then 2, then it means TLS version 2 means 1 point, oh sorry, 1.1. And similarly 1 point, so let us open notepad for a while. So from here we can see that TLS 1.0 means 3. This is encoded like this in the TLS record. So version, this 1.1 is encoded like, sorry, this one is 1. So here we have to increment it. So 3 2 represent TLS version 1.1, and TLS version 1.2, 1 2 3. So it should be represented like this. And since we are using TLS version 1.2, our protocol will be encoded like this. First byte will be 0, and the second byte will also be 03. First byte will be 03, second byte 03, like this. So note it down somewhere. So this is the identification of TLS version 1.2. Here the same thing is written. Okay, so this is the this means hello. So this 16 means a handshake record, and no, not hello, this is handshake record. Okay, then this 3 is the protocol version, and this 00 and A5. So this means this is the header. So it means the actual record, it is having this much byte of data. So A5 corresponds to 165. So the actual, this is the handshake, this is the record header, and after that we have the handshake header. So this handshake message, this is a handshake record, and the actual payload of the handshake message, it is of 165 byte. Now let us compare this with what our mbed TLS is producing. So Where is my first notepad? So here, so when we have enabled debugging with our mbed TLS, we will have all the details of what is happening inside it. So here you can see that performing TLS handshake, okay, flushing output. Now the client state is embed TLS is sending hello request, client hello. So this is what we are here seeing. It is client hello, okay. So same thing is happening here. Client hello, embed TLS, client hello. Write client hello. So this is writing the client hello message to the actual socket, the underlying socket, which is implemented by the Visnet IO driver or the internet offload driver, and that internet offload driver is actually responsible for transporting this message to our actual server. So first here they are creating a random byte, which we have seen here. So this is a random 32 bytes random data. It is creating client random data. So this is all the random data, and that is why we need a random number generator, a good random number generator support in our platform. So here it has selected some cipher suits like this, and here is the complete record what it is sending out to the network. So here you can see dumping output record sent to the network. So whatever embed TLS is sending or outputting to the network through our network communication function, which is right now handled by the Visnet IO driver or the internet offload driver. So here you can see, so here we can see 16. So as we have learned here that this 16 corresponds to the handshake record. Then after that we have the TLS version 0303. So we have noted it down that 0303 means TLS version 1.2. So our client is using TLS version 1.2, and this is done by the configuration file or the SSL config.h. From there we have configured to use TLS version 1.2 and not TLS version 1. This is 1.3. This is the latest. All right, and then we have, this is the size of our this header. So this is 3b, and after the record header we have the handshake headers. Okay, so let us see what is the meaning of these bytes, that is 010000 and a1. So this 01, this indicates a handshake message, and this corresponds to client hello. So this 01, this byte, this value, it is the constant or it is the value of a client hello message. And then this is just all these things 000a, these are the size of the message. So previously it was this header. So this header was having a payload of 165 bytes, and if we reduce these 4 bytes, so we have left with 161 bytes. So the actual header, it is having 161 bytes. So let us compare this with our, so this 1 2 3 4 5, these were the record header, and this is the actual handshake header. So this is 01. So this 01 means the client hello, and this is the number of bytes following in the packet. And after that we have the client version, and here also we will have 0303. So this is the client's TLS version, and after that we have all these bytes, or they are the client random. So 32 bytes are client random, and after that we have the session ID, which is 0 for a new session, and then we have the cipher suites. These are very important. then the compression method, extension length, everything. And after that, so this is the actual client hello message that our embed TLS is preparing and sending out to the network output record byte. So here it is telling that write record, write handshake message, and then it flushed the output. That means it sent out the buffer to the actual network. So here are the bytes again repeated here. F send returned 64. So it is sending 64 byte, and this function, that is the SSL member function f send. So this is a function pointer, that is why the name f underscore send. So this is a function pointer. So in a given platform, this is pointing to a actual function that can send data through the network, and in this case we have created a wrapper for this visnet IO driver, and the visnet IO driver is actually performing the send, and it has returned 64. That means all 64 byte has been written to the uh, network buffer, or the TCP IP buffer, which is inside W5500, and they are all ready to be sent out to the network. And then the client state changes, and this time now the state is SSL server hello. So now our client is waiting for this hello response from the server, and let us see what happens. So it is parsing server hello, it is reading the record, it is fetching the input from the network, and on network port 0 it has received 5 bytes, and now it is dumping all these 5 bytes, and these are the 5 bytes. So the first one is 15, hexadecimal 15, then 0303, and you should be knowing that this 0303, it signifies the TLS version 1.2. So we are receiving this, and if you compare it with this, so this is not okay. So that means in response to client hello, we are not receiving a server hello, because the server hello, it begins with this record header of 16, but in our case it is 15. So this is the problem, and now we have to find what is the meaning of this byte, that is 15. And I'm telling you that you will not find it in this page, because this page only show us uh, the sequence when everything is okay, when everything is perfect, what sequence is followed, but it does not shows any error or exceptional conditions. So we have to manually research about this topic. So actually here we can confirm that our sending function is working. So mbed TLS is able to properly send the bytes, and these bytes are also going all the way from our home or our office to the remote server, which may be located in some other country. So internet connectivity is okay, and we are also receiving response from our server. So every transport layer thing is working perfectly, that means TCP is working perfectly. Only the problem is with SSL handshake or TLS handshake. So we have to find about why it is happening, and we have to solve this issue. Okay, so we have to, now I will show you one another site that is more informative. So here I am in this page, and this page is from cisco.com, and the document ID is this one, that is 116181. So this is the title of this document, that is SSL introduction with sample transaction and packet exchange. So from this page we can get the idea that this page was explaining only that this record header, so the handshake header. So uh, this is record header, and it is all only mentioning this single type of record, that is 16, and the 16 is used for a handshake record. But what are the other records? So here in this page you will find the details, that types of records. So we have handshake record, so let us see. So handshake record, here we have hello request, we have client hello, and then we have server hello. So so in this page we were having some problem, and now the thing is that in the type of record we also have alert records, and this is the interesting thing. Let us see alert records. Alert records are used in order to indicate the peer that a condition has occurred. So actually a error condition has occurred. Some alert messages are warning while other are fatal, but in our case we were not getting warning, we were getting fatal errors. That means we cannot continue. You can see that a fatal alert message was received. So you can see the same thing, fatal alert record. Okay, so this is a fatal thing. So let us look here. So SSL record overview, record format. So we there are four record types in SSL. We have already seen handshake. Okay, so this handshake was starting with hexadecimal 16. Okay, so from here you can see that alert. So alert is starting with this byte, that is a hexadecimal 15, and this is what we are receiving here. So this is the data that is received from our socket, and input record from network. That means this record is read from the network, and here it is, this thing. So it is 15, and this 15 it is matching. So actually we are getting a alert from the server. That means something is wrong with our client hello or the client handshake, and this is we have to find what we are doing wrong. So let us once again go here. So as we have learned from this website, that the client hello contains the protocol version, so this cannot be a problem. Okay, the client random data, this cannot also be a problem. There is a very less chance that this is problematic. And optional session id to resume, we are not sending any id to resume. A list of cipher suites, so this is the thing, and we are not using compression methods, and we are not caring about the extension. So I thought only the cause of problem could be this, a list of cipher suites. Okay, because we are not using any compression. So let us see what cipher suites our this client was offering to the server. So here is the log, and here you can see that it has our this TLS client. mbed-TLS has selected only two cipher suites, that is client hello. So it is offering only two cipher suites, and the first one is the TLS RSA with AES 128, GCM SHA 256, and another one is the same thing but with a better AES, that is in place of AES 128 it is using AES 256 and this CBC. So I thought this could be the problem, that our client is offering means very less option to the server, and I think that these are very old cipher suites, so maybe the server is rejecting our request due to these cipher suites. So we have, I thought that I should try with some better cipher these suites, cipher suites. So I thought that my web browser was properly able to access the server, that is like this. It was is properly able to access the server, no problem, no TLS handshake error. So I thought what cipher suite this Firefox my browser was using. So let us see and try to use the same cipher suite here also with our embed TLS client to check if it works or not. But there was one problem, that this my Firefox, it was using the latest version of TLS. So if I go here and see that, and this problem is that the latest version of Firefox, it was using TLS version 1.3, but my experiment, I have already told that we are experimenting with only with TLS version 1.2. So I cannot use this cipher suite, that I will not be able to use this cipher suite in our embedded client, that means with the embed TLS library, because this cipher suite is the part of TLS version 1.3, and it will not be supported in TLS version 1.2. So first I have to change the version of the TLS which my browser is using. I have to switch it over to TLS version 1.2, then only I will be able to get the correct cipher suite. So let us do that. See that, note that Firefox currently it is using TLS version 1.3, and I have to switch it to TLS version 1.2. Okay, so let us go open a new tab and go to this address, that is about config colon config, and there proceed with caution, accept the risk, and go to TLS, and here you can see the maximum version of the TLS. So as we know that we have to set it here 3 3. So this corresponds to the TLS version 1.3. Okay, now we can close the tab and we can refresh this page like this, and once again check the certificates, connection is secure, more information, and here we can see that now Firefox is using TLS version 1.2, and we have to note that what cipher suite it is using, and currently it is using TLS ECDHE underscore RSA with AES 128 GCM SHA 256. So we will try with this cipher suite. We will instruct embed TLS to propose our server with this cipher suite so that we can get a success with handshake. Let us see what happens. So first we have to understand this naming scheme. So what does this means? TLS ECDH E underscore RSA. So for that I have opened this page in Wikipedia, and this page, uh, the topic is cipher suite. So from here we can get the naming scheme of cipher suites, and if we compare with this one, so TLS, so this signifies that we are using the TLS protocol, and this is very important. ECTHE, here we also having ECDHE. So this is the key exchange algorithm. This is very important because we are now going to enable this key exchange algorithm. This was disabled by default in our configuration, and we need this key exchange algorithm so as to replicate this request, which the same as the Firefox is doing. We want to replicate the same with our microcontroller, and after that we have few other things like RSA authentication mechanism, session cipher, session encryption key size. So first let us enable uh, so we were using this one, our client was using this one, so I think this is a bit old cipher suite that no server in modern time will accept. So we have to specify this key exchange algorithm also. So let us see if this algorithm is supported by our this embed TLS. So in embed TLS we in embed TLS we have I think in library we or include, let us first try include, we have a file called cipher suites, so it lists all the supported cipher suites. See, so here it is, bit downwards, it is called the SSL cipher suites.h. So this file lists all the supported cipher suites, and also if they are depreciated or if they are weak. So these weak ones are not gonna work, I think. Here the default configuration, these are using the older version. Let us check. Control F, find, put it here, string not found. So actually this name is not matching with the define hash define, because in hash define they are using this underscore symbol, and here they are using this dash symbol. So let us replace all the dash symbol with underscore. Now I have converted all the dash symbol with underscore. Let us see. So here it is, supported in TLS version 1.2. So now let us find this one, this cipher suite that our Firefox browser is using. Let me copy it from here and paste it here. Find a search. Okay, so thank God it is supported by mbed-TLS, the exact same cipher suite, that is ECDHE key exchange RSA with. Let us open Firefox also. So you can see that this one is exactly same RSA with AES 128, GCM, SHA 256 and SHA 256. That's great. So it is supporting, but we have to enable certain features, certain blocks of this embed TLS, so that we can use this one. So the main thing is that we have to enable this key exchange algorithm. As we know that this is the key exchange algorithm, ECDHE. It is something like elliptic curve cryptography. So elliptic curve Diffie-Hellman. So this is the key agreement protocol between two parties. So we have to enable this thing, this protocol. So how it is done? So we have to again change this file. We have to change this file, that is SSL config.h. We have to change this file. Through this we can enable and disable certain features of mbed TLS, and that's what we are going to do now. So here we have some defines that can enable this. So we will copy this thing and paste it in our file somewhere around line 28. So let us go to line 28. Here we have to put this thing, because I have already done that, that is why it is already here, but you have to put something like this. Okay, so what we are doing, we are using mbed TLS key exchange, this EC, that means elliptic 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 curve Diffie-Hellman. Don't know how to pronounce this. We have enabled this here, and these are its dependencies. So how you know, you have to define these. So uh, if you enable only this, it will show some error, because there is a file which checks the configuration. There is a file inside mbed TLS which check if you are properly providing the configurations or not. That means if you enable a feature, it will prompt you, it will warn you that the dependencies are not enabled, and from there I have got the idea. So I have enabled this key exchange method and also its dependencies. All right, now let us try to build this code, see what happens. I have started the build. Going good. Let us see what happens. Since we have modified the SSL config.h, it is compiling the whole thing. Now compilation is okay. Now let us see if this code runs or not. So let me prepare the hardware. Now I have set up my hardware, everything is ready. Now let us start the new debugging session. My debug session is starting. Now here we have a fresh new debug session. My run pointer is here. Let us also open the terminal to see the outputs. Let us run this code. Here we go. Let us see what happens this time. Oh, again we have some problems. Let us see if we can scroll up and see. We need few more rows, but it does not support scrolling this terminal. Let us clear and run once again. Scroll bar is gone here from here. I think we have to capture the outputs. So let us start the capture mode. Capture mode started. Let us and let it run for a while until we have all the data. I think capture is completed. Let us open the file. Again, it is not sending the new cipher suites. We have to investigate the issues. Again, it is sending only the old these things. Okay, wait a minute. I know the solution. Okay, so the problem was that uh, here we have again in the SSL config only. So here they have enabled certain cipher suites. Here they have selected some cipher suites. From here we have to enable this one, because let us match it with Firefox. So this is TLS, this one RSA with AES 128 GSM 256. So this is going to work, this one. So let us enable this one. It is giving, we have to enable this cipher suite. Okay, all these things are not useful. I think let us remove this, or it is better that we should remove everything from here, because if we don't explicitly select the cipher suites, then embed TLS will automatically do it for us, and this is defined here. It will select all of the available cipher suites. So we will I think we should not explicitly select any cipher suite here, because let me show you that if this thing is not defined, that means we are commenting it out, that means it is not defined. If we search this here, apt search, it was somewhere, I think it was in some configuration file. So here it is. I have found the code. I have paused and was searching for this. So this is inside this file, that is ssl underscore cipher suites dot c file. So in the c file we have to refer. So here it is checking that if defined embed TLS ssl cipher suite, which we were defining previously here. So if we are defining this thing, then it will create this variable, a static variable, and it will populate it with whatever we have provided using this. And on the other hand, if we do not provide this, it will already have all the default these things. And in case of embed TLS, that is TLS version 1.3, it will provide some additional. And in case of when it is not lesser than this TLS version 1.3, it will provide these defaults. And here we will go with this option. It will not send all this, but only the available, means whose algorithm, whose key exchange is available enabled from this SSL config. Those cipher suite will be sent to the our server during handshake. So let us see what happens. So you have to do what you have to do. You have to undefine this thing. Okay, undefine, then again build and start debugging. Okay, so let us try once again. Build started. Because this takes a lot of time, let me pause the video. Now let me resume the recording, and now I have started a fresh debug session. Let us see what happens this time. Code is executing. Great. Now it is this, you can see SSL handshake is completing. Now everything is okay, and we have that handshake wrap up and handshake complete. Everything is done. Great. Now it is the client state is reaching mbed-TLS SSL handshake wrap up. Great, we have completed the handshake. Now we are able to communicate with the server, and server is accepting our handshake. Everything is okay, cipher suites are okay, everything is okay, and we are finally able to establish a secure SSL TLS connection, and that is also using the latest version of mbed-TLS. And in the next video we will move a step further, and I will show you how to issue a HTTP GET request and actually get this data, that means this data returned from my website, and show it here in the terminal, so that we are all sure that my microcontroller is able to read this encrypted text and everything is working perfectly. And we will also do some small experiments to learn this library and this entire technology a bit more. So now let me end this video here, and we will again continue in the part 4, where we will wrap up and finish everything, polish everything. And one more thing, that I am putting all this code, whatever code I have developed during this video course, on GitHub, and I will share the link in the description of this video. From there you can download the entire code for your reference. So that's it for now. See you in the next video. Sorry, let me show you one more thing, one more interesting thing. Because the output was so long, let us capture, let us run this example once again and capture this uh, to a file. Okay, let us name it capture success, because we have got a success during this trial. Save, port is open, capture, clear this window, start overwrite. Now capture is started. Now let us go to our IDE. Where it is. And since we are already in the debug session, let us just restart the program, and I will also upload this file in GitHub, and I will share the link so that you can also analyze this file. Restart, go, and it is capturing the data. This icon is moving, and this time we have to wait a bit more, because the SSL handshake takes some times, and there are lots of output produced in the UART or the serial terminal. See, still it is moving, circulating. I think now the capture is complete. So let us go to the desktop and see the file. So here it is, our file, where it is, capture success. Here it is, capture success. Let me open the file, and here we have all the logs. So last time we were see, this is the interesting thing. Now it is, that means our client is offering these cipher suites, and this is in order of the priority. So first it is offering this one, and now you can see that elliptic curve, this cryptography key exchange method is enabled. So in both the case, it is offering this thing and this. So this one, if we match with our Firefox, this is exactly the same, that is TLS, TLS, ECDHE, ECDHE, RSA with AES 128, and then GCM and SHA 256. So our server has selected the first proposal, that is this one, and this is matching exactly with the Firefox. So now we are able to exactly replicate the request that is sent by Firefox, and now our client is also sending the same SSL handshake request or SSL hello message. and now it is working great, and it is also offering a few more these algorithms, but the first one is great. So our server has chosen this one. It is offering also better security, and this one is selected for TLS version 1.2, and everything is working great. And if you scroll, you will be able to see all the logs. This log is very long because certificate exchange is also taking place during the handshake to every. So last time we were failing here. This is the hello message, and now one minute, no, this is the our client hello, this is the client hello. Okay, this is the client hello. So we have also already analyzed this thing, and after writing the flush output, uh, here we were getting the error. Okay, here we were getting the error. Here, instead of the proper server hello, this time server is telling hello. So now when we are telling hello, our server is also telling hello. And previously what was happening, previously when we are telling hello, our server was simply refusing. It was telling that please go away, I don't want to talk with you. And this way the server was rejecting our hello. But this time you can see that server is actually sending us this thing, the hello message. So this is the proper, because this time now this is beginning with 16, and we have seen that this 16 corresponds to a record at TLS record, which corresponds to a handshake record. And if you analyze this using the website, this website, you can see that we are actually receiving the server hello in form of this. So we are receiving this 16, this is the version annotation. So here you can see that it should be something like let me open this here. So this is it. This is the sending. We have to see the receive where we are receiving. So here we can see that this is actually the message that was sending, and here that after sending this message, here we were previously we were receiving 15. That was a alert message. So now here we can see that first the port has received 5 bytes, and these are the 5 bytes. Previously we were receiving 15, and now this time we are receiving 16. So proper message we are receiving, and this correspond to a server hello. We have 16, we have 16 here, we have 0303, we have 0303, and this is different because the size of the header is different. You can see this is finally the size, and after that here we have few more bytes. So now from it is also able to pass this message, and it is able to get the version and everything. Before it was telling that it has received alert message of fatal error message. And let's see after that, this is the interesting thing. So after this record, after we have completed these 5 byte 1 2 3 4 5, so here 1 2 3 4 5, after this 5 byte we are getting this 02. So this 02, if we see that this is a handshake message type, and this is server hello. So this time our server is not rejecting our request, not rejecting our handshake. When we were moving our hand forward for a hello, it was simply saying please go away, but now it is saying hello. So this shows that the server is interested in talking with us. So we have got proper reply here, and now that it is a long thing, we cannot explain all this thing. So there is server movement, certificate movement is also there. You should go through this website okay, thoroughly, then you will be able to and compare it with this thing. So here you can also see that which cipher suit our this server has chosen. So server hello, when our this mbed-TLS is parsing these bytes, okay, these input bytes, when it is parsing this thing, then it has found that the server has chosen this cipher suite, that is C02F. This is the code. And when we go to the request, here you can see this. Please note it down, please note it down that it is C02F. So here in the top, C02F. So the first cipher suite is selected. So in this way, this is very interesting. You can go through this. Okay, when you have time, you can go through this website, go through this log. I am attaching this in the GitHub also, and I'm sharing the link in the description of this video, so you can refer there. You can download from there and go through this. And finally, this is, I think, this is the certificate, because this is very long. So I think this is the certificate exchange. This is very long, very long. I think this is the server, this is the certificate, and you can also see some text here. So these are corresponding to some of the contents of the actual contents of the certificate. Here you can see the name of the organization, everything, the organization which has signed the certificate, the validity, everything. So here you can see certificate. So if you get this kind of very long response in your serial term, so let us scroll to the bottom. And finally, I have already shown you that certificate exchange, key exchange, everything we have. Still it is very, so if you get this kind of very long log output from mbed-TLS, only we have to see that mbed-TLS client finished. So this is something is getting finished properly. This is a good indication. So we can tell that our handshake is proceeding properly. Extremely long output. So great. mbed-TLS server finished. Finished. Everything finished. Wrap up. It is also doing final wrap up. So here we can see that handshake is completed successfully. That's it. That was what I was trying to show you. That is why I continued the video. Now I should stop the video. So again, thanks for watching. See you in the next video.